Welcome, folks, to the last and final edition of the workshops. I'm Saumil Shah. I believe I happen to know almost all of you in the list. So it's going to be a nice, coffee table session for all of us. Today, I have a number of exciting hands-on things in store for you folks. I want to just go around the room and ask you, how many of you are going to participate in this workshop hands-on? Please use the Zoom chat box or use the raise hands to let me know, and I will adjust the speed accordingly. Okay, Jatan's on. Fernando, great. All right, so let's. Oh yeah, Costas. I'm sure you're gonna be able to keep up. No problem at all. This is like a very easy session. The purpose of this session is to get your feet wet and your hands a little dirty with EMUX, and show you what you can do with debugging on EMUX. Let me fire up the slides, and we're good to go in a second. And sharing the screen would help. There we are. Right. So a formal introduction. My name is Saumil Shah. I've been in cybersecurity for a very long time, more than 25 years. Today, I'm going to show and share one of my favorite projects with you called EMUX. So what is EMUX? It is a versatile firmware emulation framework that I've been building for almost 5 years in the making. Last year in November, I made a significant addition to EMUX. I added MIPS support. Well, before that, it used to be called ARMX, and most of you know me through my ARM emulation and my ARM exploitation training and research. Since November, I've added MIPS support. I couldn't call it ARMX anymore, so we have a name change, and it is now EMUX. If you wish to know more about EMUX, there is a lot of documentation that I've published on emux.exploitlab.net. I've also done a number of workshops on EMUX. I've done workshops on how to use EMUX to emulate new devices. I've done workshops on a tour of EMUX, and I've done workshops on some EMUX internals. A number of these workshops are also available online, recorded, and accessible for free. You may browse the Ring Zero Vimeo channel, and you'll find some of the workshops over there. And I will give you some more links in the Discord channel once the workshop ends. Right. So let's see what this workshop is all about. We're going to spend time talking about specifically debugging. We're not going to talk about EMUX internals. We're going to take a target, a simple-ish target. We're going to then run it under EMUX, and we'll spend the rest of the session debugging it and playing around with EMUX debuggers. Another quick show of hands. Folks, how many of you in your careers have used or suffered GDB? You can use the chat box, or you can do the raise hands thingy if you work with GDB. Right, we got Fernando. We got Costas. I know Guven's being shy, but he's definitely suffered GDB. Jatan, that's great. Okay, so this talk is going to be a lot about GDB, and specifically how you can use GDB with EMUX. We're going to talk about remote debugging. We're going to talk about how EMUX makes the whole process of remote debugging slightly less painful. Let's see how our setup is going to be like. I'm hoping all of you folks have the EMUX Docker container. You've downloaded it, you've git cloned it, and fingers crossed you've tested it. The layout, briefly to explain the environment, how it is. You have your host. Within your host, you have the EMUX Docker container. Now, whenever you run the EMUX Docker container, you have an internal networking IP address assigned, which is 192.168.100.1. Within EMUX, whenever you launch an emulated target using the launcher, it is going to spin up QEMU and bring up an emulated firmware environment. And this is hard-coded to IP address 192.168.100.2. It runs entirely within the Docker container. And within the emulated environment, you can start up the user space and launch a number of binaries that are part of the target firmware. The binary we're going to explore in our debugging session today is called nweb, which is our target binary. It's an interesting little web server that I've played with, and we're going to have some fun with it today. Whenever you're working with EMUX, you're going to have the emulated environment in one section, and you're going to have a number of shells attached to the EMUX Docker container. Think of these shells as just additional terminals on your system. You need your own workspace. So you've got a few windows open or a few panels open. And on all of these, you may launch EMUX Docker shells. I typically have 3 or 4 EMUX Docker shells floating around. And we're going to do all our hands-on work from within the EMUX Docker shells as if we are a remote attacker. And then we're going to attack the target on 192.168.100.2. So that is the overall setup. Now, how does the traffic flow work? There are a few creature comforts that we've built into EMUX simply for a better workflow. One of these things is a workspace directory, which is a shared directory. Within your EMUX setup, within your EMUX container, you will have a workspace directory, which is shared across your host. You can access the files in the workspace from within the container, within EMUX Docker shells, and you can also access the same files from your host. So if you wish to use your fancy editors like Visual Studio Code, and you want to edit files, simply make sure all the files are in the workspace directory. You work upon them, then these will be instantly accessible from within the EMUX Docker shell. If you wish to use Vim within the Docker container, just like me, you like pain and suffering, then go for it as well. About how to reach the target. Like this is a web server target. So obviously we need to be able to connect to the web server and send it HTTP requests. There are 2 ways of doing this. If you're within the Docker shell, all you need to do is make a connection to 192.168.100.2 on port 80. You can do this using curl and the command line, and you'll be able to access the web server on the emulated environment. If you wish to access the web server using a browser on your desktop, then you don't have a browser running in the Docker container. You'll have to use a browser that is present on your host. And in which case, you need to be able to reach the web server. And this is done by some internal port forwarding that is built into EMUX. When you open a browser on your desktop and you connect to localhost port 20,080, this port automatically gets forwarded to the internal web server, and you'll be able to communicate it just as if you're on that same system. This is a bit of the layout. We're going to explore this when we start up the Docker environment in just a little bit. I'm going to spend a few minutes explaining what the rest of the workshop is going to look like. Then we'll do the setups, and then we'll jump into a debugging session. Folks, at any point, please feel free to ask me questions at any time. If you wish to type in the chat box, that's great. If you wish to raise your hands, unmute yourselves and speak, that's great too. We'll keep looking at the chat box off and on. Okay, let's talk about what concepts we're going to cover in this workshop. First off, we're going to talk about what a debugger can and cannot do. What are the basic functions of a debugger, especially what we're going to explore today. Second, I want to touch upon a little bit on remote debugging. Remote debugging is slightly complicated. And if you're doing a lot of debugging, it's very easy to get lost, which will naturally lead me to brag a little bit about EMUX's debugger wrappers, which makes the whole process of remote debugging very, very easy. Fourth, I'm going to show you what Jeff is like. Jeff stands for GDB Enhanced Features. It is a beautiful Python plugin written by Hugsy. Ever since I've used Jeff, I cannot un-Jeff anymore. I have to have Jeff with all my GDB setups. Otherwise, I feel naked and lost. So naturally, when I built up EMUX, I had to make sure Jeff functionality was built in as well. So we will use Jeff and I'll show you what Jeff is. And the rest of the workshop, we're going to work with the NWeb binary. We're going to do some debugging. We're going to do some tracing. We're going to do some breakpointing, and we're going to do some crash dump analysis. Fine. Let's get to these things one by one. What does a debugger do? Debuggers are meant to slow down the process execution. By slowing down, what I mean is debuggers will let you control process execution the way you want. You want to stop it, you want to resume it, you want to inspect things that are happening while the process is running. Debuggers support all that. Essentially, debuggers are for any type of interactive runtime analysis. Few of the popular features that every debugger will offer you allows you to inspect the target, allows you to inspect the CPU state, allows you to examine the memory of the process, allows you to control the process execution. You can single step, you can jump. Sometimes you can even go backwards. You could do reverse execution. A number of modern debuggers support that. And then you can analyze crash dumps, you can analyze exceptions. And nowadays, most debuggers will come with a few luxuries to make our life easier and automated. We have some plugin features, we have macros, and we have logging. Okay. I'm going to now show you or talk to you a little bit about remote debugging. But why am I going to talk about remote debugging? Whenever you're dealing with firmware and emulated devices, this is not like your desktop environment where you can load a debugger right onto the emulated device. If say you're playing with some Windows binary, you can just use WinDBG on the same host that you're playing with the binary that the binary lives on, and you can run the binary and attach WinDBG to it and use it interactively on the same environment. In case of IoT devices, you don't get the luxury of loading a whole debugger on the target. Instead, you'll have to be able to send a debugger stub, which runs on the target. It's a very small bit of program, very lightweight, very compact, and it hooks into the process you want to debug. And then using inter-process communication, mostly TCP/IP, you can connect to a full-fledged debugger environment on your host and then control the target using the remote stub. So on the left-hand side of the screen, of the slide, you see GDB multi-arc, which is GDB that supports multiple CPU architectures. You may be running on an x86 system and you want to debug an ARM binary or you want to debug a MIPS binary. Well, plain simple x86 GDB won't do. You need a multi-architecture GDB. The GDB itself runs on an Intel platform natively, but it has the capability to debug ARM targets, to debug MIPS targets, to debug PowerPC targets, or whatever other features it's built in with. So we're going to use GDB multi-arc on our host. Our target is running on 192.168.100.2, which is the remote host, and we're interested in debugging the NWeb binary. We're going to use the ARM version of the NWeb for the first part. Time remains. I'll also show you the same thing in MIPS. So on the remote host, we will run GDB server. The GDB server is that small debugging stub I talked about. You have to have it copied onto the remote host somehow. You invoke it on the remote host and make GDB server attach to the process ID of the binary you're interested in. GDB server can communicate with the host in a number of ways. And the most typical option is to have GDB server listen on a TCP port. In this example, you see it is at port 5000. And the way you're going to connect to the GDB server is from your desktop debugging environment, you tell GDB multi-app, hey, where's the remote system? The command to be used is target remote, and then you provide the IP address of the host, the remote host that GDB server is running on, and the port number that it is listening to. Now, once GDB is issued with the target remote command, it will connect using its own GDB server protocol, and then you will be able to remote control the debugging session of the target binary through your desktop environment. Now, you also need to do a number of things in order to get a smooth debugging session going. Like, you need to be able to tell GDB where the file system is on the remote host, what symbols need to be loaded so that you get a better debugging experience. And there are some environmental setup commands like set sysroot target and the path to the root file system. Once you've set up the environment, once all the symbols are loaded, then you're ready to begin the debugging session. Now, this is typical for a lot of remote debugging sessions, right? You're going to be doing this repeatedly if you're debugging and analyzing a target. It can get very painful and difficult if you have to do this whole thing again and again. Like for me, if I'm doing an exploit development session and I'm working on an exploit, I'm going to be having to attach the debugger 20 to 30 times during any given session. Like, try it, it crashes, you start the target again, it crashes again, you keep on attaching the debugger and you keep on doing debugging sessions. If you have to do all this stuff like launch GDB server, do a target remote, set sysroot, it gets very tedious. And for a person like me, whenever things get tedious, I tend to make mistakes. I tend to slip up, and then you waste time. So when I was building EMUX, one of the things I wanted for me and my students was a very smooth debugging experience. And therefore, I wrote a few wrapper scripts. Let me show off a little bit what you get with EMUX GDB. So now when you're debugging with EMUX, you don't need to do this GDB server business and this GDB target remote thing. Everything is wrapped into one command called EMUX GDB. All you have to do is from your Docker shell, you run EMUX GDB, you provide it with the name of the remote process, because I'm too lazy to look up PIDs. And then EMUX GDB does everything else. It will look up the PID of the target. It will automatically launch GDB server on the remote host. It will launch GDB multi-arc on your desktop, connects to the remote GDB server, sets the sysroot, sets the environment, and you're ready to debug. Everything else is taken care of behind the scenes. And we're going to make heavy use of EMUX GDB. This makes it almost like you're debugging on the same environment. You see no difference whatsoever. All right, next up, I want to show you what Jeff looks like and why I am so happy about Jeff. Jeff is something which I've fallen in love with. On the left-hand side, you see a crash dump using plain old GDB. You get a crash, all that GDB is going to tell you is that, hey, you have a crash. Then you literally have to like worm out information from GDB. Okay, now that is a crash, what are the registers? Show me the registers. Okay, I'll show you the registers if you ask me nicely. Type a command info registers and shows you the registers. What else do you want to know? You want to see the stack? Okay, then you have to give some examine commands to show the stack. Now, whenever you're a reverse engineer or exploit developer, there are a few things you want to do every time when things crash in a debugger. Like, I want to see the registers, I want to see the stack, I want to see where my code is. And these are a few default things that everybody needs. So Hugsy, when they built Jeff, thought of all this. And what you see on the right-hand side is the same crash dump with GDB using the Jeff plugin. Whenever things crash, you automatically get a dump of the registers. There's beautiful colorization. If a register has changed, it takes on a different color. If a register looks like it is a pointer to a string, then there's some automatic dereferencing going on, shows you the string. If a register seems to be pointing to an instruction, it will disassemble the instruction and show you. Below, you have like a little bit of the stack, like what the stack looks like, what are the words on the stack. Then it shows you the call trace. It may also show you the next few instructions that are coming up. And this makes your debugging session very efficient and smooth. Okay. 2 slides to go before we start getting into the hands-on sessions. These are the core concepts I wanted to cover. What are we going to explore today? Today's target is NWeb. It is a web server, which I've actually found on some production systems, like devices. This web server contains a vulnerability. We're going to embark upon a little bit of a treasure hunt to find out where exactly in the NWeb code does this vulnerability lie. We do not have the source code of NWeb. It is fully black box, as if it's just come with the IoT device. Now, we're going to use our debugging skills to perform 4 things. We're going to see how to perform reconnaissance on the target binary, study the binary, study what the binary offers. Bulk of our time we're going to spend looking at the way processes are executed, the binary is executed, starting and stopping it, pausing, resuming, breakpoints and such. While we're stepping through the binary, we're in different stages of execution and tracing. We're going to inspect a lot of internals of the binary. We're going to inspect the state of the CPU registers. We're going to inspect the CPU flags. We're going to inspect the stack. We're going to inspect function call frames. We're going to inspect memory in general. We're also going to disassemble a few things and study where we are in the whole execution map. And lastly, we're going to use some luxurious features that GDB and Jeff provide us, which will allow us to log lots of output to a file and also allow us to automate parts of the debugging process. So I chose this NWeb example to give you a good introductory start into basic debugging sessions. My objective of this workshop is to enable you to perform debugging on a target and follow this kind of a process to help you get moving with it. There's a lot more you can do with it. We can do like a whole 4-day training on GDB by itself. This is not the objective of the workshop. I also want to make a note at this point that this workshop is actually a small subset of the training that I'm going to offer in Las Vegas coming up in August as part of the ARM IoT Exploit Lab. So this workshop gives you a feel for what my training classes are like. A few EMUX utilities. We're not going to use all of these, but these are some helper functions, some wrappers to make remote process management and analysis and debugging easy. We're going to use EMUX PS to list processes on the emulated device. We're going to use EMUX GDB a lot because this workshop is all about GDB. And then we'll use EMUX halt when we're done with the GDB sessions. If you wish to read more about EMUX utilities, all this is available on the EMUX website in the documentation. We finished with the initial part of the workshop. We're going to do a little bit of setup. I'm going to go slowly. I want to make sure that we have launched our target environment and we are exactly where we need to be before we begin the NWeb debugging sessions. Quick show of hands, folks. How many of you have your EMUX Docker containers started up? You may either raise your hands or you may paste in the chat box. All right. Fernando, Guven, Costa. Okay. A few administrative notes. Sherry has reposted the URLs for the slides on the Zoom chat box. She's also posted the URL for the live notes, which I will use to type in the commands and paste them as they go along. So at the end of the workshop, you have a running transcript of everything that we've done. Okay. So first step, from your host, you want to start the Docker container. And this happens using run EMUX Docker. Let me do this while we'll launch a terminal. I already have my EMUX cloned and I've built the Docker setups. So I'm going to do a run EMUX Docker. It's going to run these few commands, and towards the very end, you should see this EMUX Docker prompt, and this is going to be our main Docker console. The next step from here, we're going to run the launcher. The launcher is the main component of EMUX. It brings you a menu. And in the menu, you see a list of devices that are emulated within EMUX. We're going to select the damn vulnerable ARM router. And we're going to click OK. This is going to boot up the kernel side of things for the damn vulnerable ARM router. I'm going to do this side by side. We'll run the launcher, hit enter. You get this menu and select the first item itself, damn vulnerable ARM router. I'm going to do it again. I believe the screen sharing was on a different environment. My error. So let me open up a terminal. I'm going to go to EMUX. I'm going to do a run EMUX Docker. I'm going to do a launcher. And we're going to select damn vulnerable ARM router. When you do that, you will see the kernel boot up. And eventually it will drop you into this EMUX device console. It tells you a few things. Like this is an ARM v6 processor. It's running like an ARM 11 MP core board. It's running Linux kernel 3.1.3.18. Once we've done the launcher bit, we're not going to touch this part at all. Okay, let me minimize this. And let me open up another window. What we're going to do now is we're going to launch the user space side of things. Let me show you the slides for a bit, and then we'll go do the hands-on. So launcher is running. Next, what we're going to do, we're going to open a new terminal window. You may open multiple terminal windows if you like, or if you're using a program that can split the terminal windows into multiple panels, you do so as well. I usually use like 3 different panels. And in each of the panels, I will launch an EMUX Docker shell. This will like gain me one more shell access into the Docker container. And in one of these shells, I'm going to launch the user space command. The user space command is going to bring up the user space menu. You'll see a menu like this. Once you see this menu, you go to the very last option, which says enter DAM vulnerable ARM router console exec bin sh, and select that. Do not make the mistake of starting the DAM vulnerable ARM router. If you do that, you have to like shut it down, and then we have to start this process over again. So I'm going to do this step by step, and then 2 steps will be ready to play with NWeb. So let me run the EMUX Docker shell. We'll run the EMUX Docker shell over here as well. In this EMUX Docker shell, and let me also submit this. I need one more. In this EMUX Docker shell, I'm going to run user space. I'm going to hit enter. And this will bring me the user space menu. You want to make sure you select enter DAM vulnerable ARM router console. You can hit enter. And you'll see if you debugging messages, and at the end, you will be on a BusyBox shell prompt, which is part of the emulated router environment. And you can do cat proc CPU info, and it'll show you that it is running on an ARM v6 compatible processor. Okay. Once you're at this BusyBox prompt, we're going to manually launch the NWeb web server. I'm going to go back to the slides one last time and show you how to launch the NWeb. And then we'll return over here. At the BusyBox prompt, you need to invoke NWeb manually using the command NWeb. Then the port number is 80, and the web server root is /www/nweb. When you run this command, nothing will happen, but the web server will have started. And then from the other Docker shell, we're going to use curl to test whether the web server is up or not. If everything works fine, you should see a message like ring 0 hack me appear when you run curl. Let me do that. First, we're going to run NWeb over here. NWeb port 80 /www/nweb. Press enter. If you want to see whether the web server is running successfully, You can use EMUX PS, grep nweb. And it'll tell you that nweb is running with PID of 579. You want to see what ports are listening on the target? You can use EMUX netstat -NL. And it'll tell you that port 80 is listening on the target. Lastly, let us test whether the web server is functioning correctly or not. We're going to use curl HTTP 192.168.100.2. And you hit enter, and you should see ring 0 hack me as a response. In the nweb directory, in the BusyBox console, I apologize, actually there's a train passing next to my office and it's making a blaring noise. So apologies in advance for some horrible interruptions. I'm going to mute for a moment until it thunders past. I've been doing these Ring Zero virtual trainings and workshops for a number of times, especially during the pandemic. There are always a few things that happen all the time. One is nowadays a train thunders past at about this time of the night. And at about 11 o'clock India time, the street dogs start barking outside. Pretty much on cue. They're always like within a minute. The dogs bark, it's 11 p.m., and they make a racket. So this thing happens. All right, back to nweb. In the BusyBox prompt, if you go to /www/nweb, you will see there is a log file created called nweb.log. You cat nweb.log. It'll show you the requests and the responses. I have some old stuff hanging around, so I'll remove nweb.log. I'm going to do this again. And this will show you some requests and responses that just happened. This means nweb is working quite well. Now we're ready to work on the attack side of things. First, we're going to just grab the attack binaries. We're going to use them a little later. Now, in one of the EMUX Docker shells, go to the workspace directory and wget the attack scripts. I'm going to paste this on the live notes as well. Okay. From here onwards, everything we do, we're going to do within the workspace directory. So I'm going to go change to the workspace directory in all these remote shells and everything. Let me wget attack1.py. You grab it, and then you make it executable. So I went to the workspace directory. I'm going to wget the attack1.py. The URL is pasted on live notes. You grab it, and then you turn it executable. Chmod plus x attack1. This completes our baseline setup for this workshop. The rest of it is going to be all hands-on from now until the end of the workshop. Let's get started with the hands-on stuff. Now that we have the nweb binary running, we want to follow a step-by-step process. First, we're going to check what this binary is all about. We're going to reconnaissance the binary. We're going to do a little bit of footprinting. We're going to find out the process memory layout. We're going to find out which libraries it loads. And then we're going to find out what functions does this binary contain. Our goal, remember, is to find where exactly is a buffer overflow located in this nweb binary. We're going to test it iteratively using curl, and then eventually we're going to attack it using the attack1.py script. So let's get begun with the GDB sessions. Let me open up. Let me leave this user space as it is. I'll minimize it, and I'll open up yet another window so it stays clean. In this one, I'm going to divide it into two parts, both to run EMUX Docker shell. Always say you can never have enough EMUX Docker shells. Each of them switch to the workspace directory. The top panel I'm going to use for all our GDB stuff. The bottom panel, I'm going to run curl, or I'm going to run the attack scripts. So first, let us see if EMUX, if nweb is running. I'm going to do EMUX ps grep nweb. nweb is running. Now we're going to attach GDB to it. So we're going to do EMUX GDB nweb. You can see GEF for Linux is ready, and it's loaded. It's connected to the remote. You can see all these commands are automatically issued. It connects to the remote. It changes the path, the sysroot. It reads all the symbols. It shows you where it is paused. Here is the dump of the registers. Registers are displayed automatically. The CPU flags are decoded. This is a beautiful nicety that GEF offers. Down here, you have a stack view. This is the top of the stack, and these are the top 8 pointers on the stack. This is the code view. This is where you are in the code. The current instruction executed is indicated by an arrow. And right now we're stopped at a syscall. And this is where you are in the code. You are within main. This is the call stack. The trace section is basically which function you're in and who have you been called by. So you're in a syscall and you've been called from main. and the rest of it is all symbols. And right now, we're ready and we're good to go. The first thing we want to do in footprinting this is we want to check the process memory layout. Where does this binary live in the address space, and what else is loaded with the binary? So to do this, we're going to use a command that is supplied by Jeff, and it is called vmmap. Running vmmap will give you a list of the various modules that are loaded in the process memory. Now, this is a 32-bit target. The process space userland of the process space goes from 0 to BFFFF, which is like about 3 gigs. And here you can see that these top 2 entries, these are the binaries. I mean, this is the binary NWeb. The first entry is the text section. The second one is the data section. Then you have the heap. All this stuff that you see over here, these are the shared libraries. There are 3 libraries that the NWeb binary is linking to. One is the loader library, LD uclibc. Then there's libgcc. And then there is libuclibc, which is the main C library. And the bottom, you have the stack of the process. This is rather typical. We can further inspect the binary if you're interested in the details of the ELF section and how the binary's various ELF sections are. You can run info target, which shows you this is the entry point of the NWeb binary. This is where the first instruction starts from. And the table over here shows you which other ELF sections exist in the NWeb binary. For us, I mean, this is nice to know. It's not super important. I always make it a point to look at this just in case I miss something. Let us also look at the shared libraries. You have once again the use of the info command. Now, info is a built-in GDB command, and you can use the info command to get information about a number of things. At any point, you can also use the tab, like do double tab, and it will show you all the possible sub-commands that the info command offers you. So we saw info target. Then we're going to see info shared library. And then after this, we're going to use info functions to dump out all the functions. Let's use info shared library. This tells you what shared libraries are being used. Like I said, there are 3 shared libraries. And lastly, we're most interested in all the functions that are provided by NWeb. Again, our goal is to figure out where exactly does the buffer overflow lie. So we go from binary, we break the binary down into smaller components, namely the functions. And then eventually what we're going to do is we're going to set breakpoints at these functions, trace through the execution, first understand the functionality, and then we'll see where things crash. And we'll keep narrowing down from binary to function, and then down to the very instruction that the buffer overflow gets triggered. So that's what I have in store for you. Let us now enumerate the functions that are present in this binary. The command is info functions. Now you'll see some information like this. There are a number of functions which end with the suffix @plt. To cut a long story short, PLT stands for procedure linkage table. What is a PLT? Basically, all these functions that end with @PLT are not implemented in the binary. NWeb does not implement printf. NWeb does not implement getPID, doesn't implement putS, socket, abort, accept, write, bind, shader, signal, read, string, and compare. All these functions are provided by the C library, libuc, libc. They're exported, which means they're shared, and any binary can import these functions and use them. Whenever functions are imported, they're present in a procedure linkage table in your binary. So this tells us that NWeb is using a number of these C library functions. These are all the C library functions that NWeb uses. There are much more, but these are the only C library functions that NWeb uses. Towards the last part, you will see 3 functions which do not have an @PLT at the end of it. These are functions implemented within NWeb. These are the core functions that NWeb implements. It is a tiny web server, so essentially there are only 3 functions. There's main, which of course is present in every binary. There's a function called web. We don't know what it does, but it does something web-like, I'm sure, because of the name. And there's a function called log, which we can guess does logging stuff. We also saw the web server log, so I'm guessing this is what's contained in there. Now, if you are into static reverse engineering, you can take this binary and decompile the code using Ghidra, and you can statically find out where the problems are, but that's not the objective of the workshop. We're going to do these things dynamically through a debugger. What we're going to do next is we're going to now let this program run, and we're going to see what happens when we make a web request. When we attach to a program, when we attach to a process, the process is frozen. It is paused. It is waiting for input. We now want to set the process in motion once again. So one of the process execution commands in any debugger, including GDB, is to resume execution. This one is continue, or you can use the short form C to continue. It now says continuing, which means the binary is running, and every interaction we perform with it, if there is a crash or if there's a breakpoint, we'll see it in the debugger. So continue the execution, and in the other EMUX Docker shell, we're going to now run curl to make a single web request to see what happens, or does anything really happen inside of GDB. Okay. So process is running. You now have curl. I'm going to use the -v to increase the verbosity to show you the request and response. Curl -v HTTP 192.168.100.2. And I'm going to hit enter. So when curl runs, you'll see it's trying, it's connected. This is the GET request as it's sent. This is the HTTP response that it received. And the output of the HTTP response is ring 0 hack me. What happened on the debugger side of things? We're seeing something in red, which means, oh, there's some problem. Red's no good. There's no problem really. If we read through the messages, here's what it does. Attaching after thread fork to child thread. So the web server is waiting. It has forked a new child process. Many servers are like this. They'll fork a child process. The child process handles the incoming connection. The parent just waits and keeps running. So the child process ran, that is PID 1485, detached from the parent, served the request, and the child process exited. And now the debugging session is over. The moment you have a red Jeff cron, you're no longer attached to the target. Your request has ended, the process has ended. Now, there are two things going on. The parent process is not dead, it's continuing. But the way GDB is set up in case of EMUX is it will automatically follow execution to the child processes. So you attach the parent invokes a child process, the debugging session shifts to the child. If you want it not to shift to the child, there are some debugging configurations that you can perform. We're not going to get into that at the moment. Now, once the child process has terminated, the debugging session also terminates. It does not go back to the parent. If at this point I run VM map or something, it says, nope, no debugging session is active. So at this point, you just got to quit the debugging session using Q to quit, wait for a couple of seconds, and then attach EMUX GDB to NWeb again. Now imagine this, if you have to do this with a remote target, then you have to run GDB server, run GDB, set target remote, set sysroot. All this pain is now gone. Just launch EMUX GDB with NWeb. It'll find the parent. It'll attach itself again. And then you hit C to continue. You're ready for a second round of debugging. Okay. We saw that EMUX GDB had a couple of functions that it exported. 3 functions that it exported. Let me interrupt GDB and dump the functions again. I'm going to do info functions. What we wish to do now is we wish to study which of these functions gets called and in what sequence. We have main, we have web, and we have log. Main, we're already running, so no point in hooking to main. We're going to set a breakpoint to log, and we're going to set a breakpoint to web. And then we're going to run this curl request again to trace what happens, which function gets called in which order. We're so far just studying the functionality of NWeb and trying to understand what these functions do. Okay. Let me set a breakpoint. I'm going to set a breakpoint to web. And I'm going to set a breakpoint at log. So you set 2 breakpoints. If at any point you've forgotten which breakpoints you've set, you can always use the info breakpoints command, and it'll tell you how many breakpoints have been set. Eventually, as you're executing the process, it'll also tell you how many times each breakpoint has been hit. Sometimes it comes in very, very handy. Now that the breakpoints are set, we will continue with the execution of the process. And then we're going to run the curl command again. Here we go, curl. We'll remove the -v. Let me keep it -v, why not? Now, when you run it, you see curl has not finished. It has sent the request. It tried, it connected, the request was sent, and no response has been received yet. Inside GDB, you're now at a breakpoint. It says thread 2.1 nweb hit breakpoint 1 in the function web. Okay, great. So now we know that web was the first thing that got called. I mean, here are the registers. Here is the stack. Here is the code. And it says that nweb was stopped in web. Reason is a breakpoint. I want you to look at this section called trace. This shows you where you are in the process execution from a function standpoint. Okay, there's a question. This question in the chat. Question is, can you use Ghidra as the GDB client? Or what about other GDB clients? You can use Ghidra as a GDB client. Have I done it? No. Has Jeremy Blackthorne done it? Yes. He was talking about it yesterday. What about other GDB clients? I'm not too sure. I know Radare claims to do everything, but Radare is Radare, and I get scared of Radare. I have not used IDA, but I know that definitely IDA can communicate very well with GDB server. Hope that answers your question. Okay. So here we are within the function web, and this function was called by main. Now, what are these two numbers? 109 BC, 1128C. These are return addresses. Basically, these are values of the program counter. The first one is the value of the program counter you're currently in. So you're within the function called web. And then once web returns, it will return the program counter to address 1128C, which is within main. Let me confirm where we are currently. If I scroll up and take a look at the registers, I see $PC equals 109 BC, which is currently within web. And then this is the return address 1128C. At any point, you can get this information using the backtrace command as well. Backtrace shows you exactly this, the call stack. This is called the call stack. The topmost function is what you're in currently, and the functions below it are who called you. Stack trace and backtrace is very important. I like it. I like to keep my eye on where I am at any given point of time. We're still at the breakpoint. We're not done with the request yet. So now we're going to hit continue. And we went to another breakpoint. This time around, we went to log. So it hit breakpoint 2 in log. Here, if you look at the registers, you can see some of the parameters which are being passed to log. If you know about how functions work in ARM, R0, R1, R2, and R3 are arguments that are passed to the function. You can see there are two strings like request and this big get request. These apparently will be sent, these are being sent to this function called log, and log's going to do something with it. Down below, if you look at the call stack, you see now you're within log. Your current program counter is 107EC. Once log returns, you'll be returned to the return address within web, which is 10AB8. And then it's going to return to 1128C. So now your call stack has three functions on it: log, called by main, log, called by web, called by main. Where is all this information stored? How does the debugger know which is your call stack? Like, where does it find it? Well, all this information belongs to the process stack. It's a part of the stack memory. Whenever you're running functions, functions make use of the stack memory. And the stack memory saves a number of things. For every function, you have a frame created on the stack. The frame will contain a return address. The frame may or may not contain parameters that are passed. The frame will contain other registers that need to be saved and restored for the function. And the frame will contain local variables. The debugger is built to walk the stack. It recognizes each frame and then parses the frame and tells you where the return addresses are, and it reconstructs the chain of calling functions. That's what it does behind the scenes, and that's what the backtrace command also does for you. We're still not done with this code. The curl is not yet returned. We are at another breakpoint. We now type continue again. We hit log for a second time. This hit log once again. Now you can see the arguments are slightly different. You have send and index.html. In another breakpoint, you see that the return address has changed within web. Here a different return address. So log must be getting called twice from within web. And finally, we hit continue. Once we hit continue, you see the response has been sent and curl ends. The process also ends. So after this stuff, you saw we hit 3 breakpoints. We hit 1 breakpoint in web, and we hit 2 more breakpoints in log. Let's check out what we want to do next. This is a small binary. What we just did is a very rudimentary process called function tracing or hit tracing. The idea with hit tracing is whenever you study a binary, you just want to see what functions are called in what order through normal requests and response. You just want to trace the normal behavior of a binary. Because it's a small binary, we have limited number of functions, and we just hit the breakpoint thrice before the binary ended. We are able to manually step through it. You got a breakpoint, you make a note of it, hit continue. You got another breakpoint, make a note of it, hit continue. We can do that. If it's a largish binary, this business will get tedious. We would really, really like to automate this process. So next, what I'm going to show you is how do we automate the process of tracing through the binaries. We want to do the same thing, except we want automatically to continue whenever we hit a breakpoint. All we want to do is sit back and watch a movie. Okay, this happened, that happened, done. Interesting thing, I read somewhere on the internet, what is the best debugger? Sometimes the best debugger is nothing but a carefully chosen set of printfs inserted at various points in your program. And I've been doing this a lot when I used to code, like printf1, printf2, printf3, printf4. So you just see 1, 2, 3, 4 occurring. You know this stuff is executing. This quote was by no other than the Unix god himself, C god himself, Dennis Ritchie. What we want to do with GDB is exactly this. We just want to see which functions are hit, and we don't want to interact with GDB for that session. Let's see how to automate things with breakpoints. We'll quit GDB, and we're going to reattach GDB. Get used to quitting and reattaching quite a lot. I'm going to paste the next set of stuff inside live notes so you can follow. We're going to set the breakpoints again, but along with the breakpoints, we're going to we're going to associate a set of commands to be executed every time the breakpoint is set. So we're going to do first break log, right? Breakpoint 1 is set. Then we want to use the commands command. It's actually called commands. The commands command will tell GDB what commands to use when this breakpoint is hit. So it says type commands for breakpoints one per line, end with a line saying just end. All right, that's absolutely useful. The first command I want to run is continue. So, okay, breakpoint is hit, let's continue. I don't want to run any more commands. So end over here. I want to set another breakpoint at web. Again, every time this breakpoint is hit, I just want to continue. So I set commands, continue, and end. Both my breakpoints are set. I'm not too concerned about main because main's already running. And now let me resume execution after setting the breakpoints. Let's continue over here. And once again, we run the curl command. Here we go. You'll see a lot of things flying off on the GDB screen. So be ready to scroll down. Number of things happen. Okay. I'm going to scroll up all the way. Go past all these register dumps. Basically arrive at this point just after continuing. Now there's some glitches in the way GEF is handling the output. Typically what happens is every time a breakpoint is hit, you get this register dump, which is called the context, the register stack, code, and frames. This is called a context. So every time a breakpoint is triggered, you get the context view, and then it goes to the next breakpoint, you get the context view, you get the next breakpoint context view, and happens. For some reason, which I don't know, even I tried with the latest version of Jeff, is all the GDB output happens first, and all the Jeff output happens later. So I tried turning things off and on, wasn't too successful. So I just say, okay, you know what? We're going to ignore the context output. We just want to focus on this stuff. And now let's see what we got in this whole process, right? You see these breakpoints that got triggered. First, it hit breakpoint number 2, which is in web. Then it hit breakpoint number 1 in log. And then it hit breakpoint number 1 in log again. And then the process ended. Now, if you're doing this with a new binary and it's slightly complex, it might take some time. You want to record this output in a file where you go and have a cup of tea or coffee. And then you come back and you see a long trace of all the functions that happen. We'll get to this file stuff a little later. Well, let's step up the complexity just a little bit. In fact, let's kind of do it now. We want to know a number of things that happen. When we are at these breakpoints, web and log, we want to grab a snapshot of the calling frame as well. We want to do this backtrace. We want to see where we are being called from. And we want to say dump all this output to a file. So next up, I'm going to show you how to do this, how to get better at tracing and logging the data. I'm going to quit GDB. I'm going to show you another interesting way of setting breakpoints as well. Go back to EMUX GDB and web. I'm going to do info functions. We want to set breakpoints to log, web, and main. Basically, we want to set breakpoints to every function that is a part of the binary. In the previous session, we did this manually. We went and set breakpoints one by one. And for every breakpoint, we set the commands. Now imagine if this has 20 functions. You can't be bothered to set breakpoints 20 different times. And for each breakpoint, you set the command like continue. That's going to get a little too cumbersome. So to do this, we're going to use a command that performs multiple breakpoints in one go. It's called rbreak. And the R in rbreak stands for regular expressions. rbreak can set breakpoints at any function that matches a regular expression. So you want to set breakpoints to every function which has letters A through Z. Excuse me, letters A through Z in lowercase. So I'm going to set rbreak caret, which is the beginning, A through Z, and dollar, which is the end. Sorry, it is a single character, so no functions. rbreak A through Z, and then star, and then dollar. My regular expressions are a bit irregular. Now you can see that automatically 3 breakpoints got set at log, at web, and at main. This is great. This sped up our breakpointing functions rather quickly. And now we want to associate commands. Now the beauty is you can use a command by itself. When you use it, it's going to say type in commands for breakpoints 1 through 3, 1 per line. This is great. Whatever I type over here will be associated with all these previous breakpoints. Makes our job a lot easy. Now, what are the commands I'm going to choose? I'm going to paste this stuff in the notepad, in the live notes for you to refer to while I do it on the screen over here. So the first thing I want to do is I want to write the output to a file, and I want to write only selected output. I don't want all sorts of garbage in there. I'm going to say set logging on. Then I'm going to print the program counter, print $PC. This is a register. I can output it. This is going to get logged. I'm going to run backtrace, dump the call stack. Then I'm going to draw a line below it because there'll be multiple of these. I'm going to use the echo command to draw a line with a new line symbol at the end of it. And this is all I want to capture for every breakpoint that is set. I'm going to turn logging off after this. Then I'm going to continue. And then I'm going to end. So once again, we set 3 breakpoints using rbreak and a regular expression at log, at web, and at main. For every breakpoint, we're going to run a number of commands. We're going to enable logging. We're going to print the program counter in the log file. We're going to print the call stack in the log file. We're going to draw a little line that separates it from the next breakpoint. And then we're going to stop logging. Then we're going to continue. And then that's the end of the multiple commands. Now, we need to provide GDB with a path to the log file. So we're going to say set logging file in /temp trace1.txt. If you don't set the logging file, it's going to create a file called gdb.txt, and where it creates it, it will create it like some crazy location. Now we're ready to continue. We hit C to continue. And let us run the curl command once again. You'll see a whole bunch of output that happens. You get all this data that is dumped, which is fine. Let's go and see what get captured in the log file. So after we run curl and it ends, we're going to take a look at the log file. So here we are. The first program counter was at 109 BC, and the call stack shows you're in web, which was called by main. Next, you're in log, which is called by web, which is called by main. Third, again, you're in log, called by different location in web. Notice the difference in the return addresses between these, and then you're back in main. So far we saw how to profile a binary, how to discover the functions present in the binary, and we set breakpoints and trace the path of the execution to show us how the functions are called, in which order they were called, and until the binary ends, and we saw how to automate all this. Now we want to get a little deeper inside the functions. So far we've only enumerated the functions. We want to now look at a little bit of these mystery of these return addresses. Where are these return addresses? We want to get a little deeper into the function itself. We now want to check the frames for every function. Before we go ahead and do this, I want to take like a couple of minutes and see if anyone has any questions up to this point. How's everyone doing? Life's good? You're all happy? Take a minute to see if there's any questions that pop up. Okay. No questions, which can mean either one of two things. Everybody is going swimmingly, or I'm flying in a different orbit. Oh, here's one. Michael, are there any commonplace functions you see beside log, web, and main? Let me try and understand this question a little correctly. Okay. And which architectures that give you difficulties? All right. Every architecture gives me difficulties. There are some implementation quirks in each architecture. For what we're doing with this workshop, everything's going to run swimmingly on ARM or MIPS or even x86. But if you start getting into some esoteric stuff, you'll see sometimes things don't work exactly as advertised. Things are a bit glitchy. There's about 1% of things that cause problems every now and then. To come back to your first question is, are there any commonplace functions you see besides log, web, and main? Let's do an info functions. Everything else over here is like PLT, which is library functions. This one is global destructors. These are built-in functions with the ELF binaries that the compiler provides. These are not user-coded functions. No, this is all PLTs, so these are all pulled in from the libraries. The only three functions which are implemented in NWeb are these three. When it comes to regular expressions, we did this RBreak, and I used a very simple regex like A through Z, star, and $. Now, this sometimes may not cover all functions. If a function has a number, if a function has uppercase, it has underscore, it has hyphen, then it's going to miss it. A thorough and a more tighter function tighter regular expression to use for R break would be something like this. Like you want to start and you want every function which does not include the @ symbol. So it will drop everything with an @ which means it drops everything with an @plt, but includes everything else. Now, this is a better and a tighter regular expression. Should you wish to use it on code which has variations in functions nomenclature, if they don't use the preferred nomenclature, then you use this one. Okay. Yes. Right. Let us now go into looking at function frames. Again, we're going to break at web and we're going to break at log. The objective of this debugging session is to study where exactly is the return address stored. And we're going to use some examination commands to look at a few bytes in the stack and map how each frame looks like. Now, there's a lot that can be talked about frames. We're not going to dig into that level of depth. I'm going to assume that you folks know a little bit about functions and frames. So first, we've attached GDB. Let us set our usual breakpoints. We're going to set a breakpoint to web, and we're going to set a breakpoint to log. I'm going to place this in the live notes. Break web, break log. We're not going to set any commands. We want to actually stop at these breakpoints and inspect the frames. And we continue. Again, we run our curl command. And we'll find ourselves stopping at a breakpoint. Right, we stopped at web. First things, let's look at the back trace. We know what it's going to be like. It's like web and called by main. Now I told you, like, how does a debugger decode this back trace stuff? It goes through the frames of the function, and from parsing the frames, it'll come to know where the return address is and so on. If you want to study the frame in a little bit of detail, we have a function called info frame. Info frame by itself will show you the topmost frame, which is frame number 0. You can also be very specific that you want info of frame 0. You can give an index number and it'll show you the information for that frame. It's going to do info frame 0. And here it says that the stack frame is found at memory address BEFF FA58. This is the base of the frame. It says the current program counter is 109 BC. In the web, the saved program counter, this is the return address. The return address is saved as 1182C, which is the point where web will return back to main after it is done. And then it says it's called by a frame at FA90. This is the list of arguments. This is a list of locals, stack point of the previous frame. And here it says that it has saved registers R11 at FA50 in the stack and the link register at FA54 in the stack. If you do info frame 1, now you see that frame 1, that is a frame for main, it begins at FA90. You can see the linkage over here. Frame 0 was called by frame at FA90. And this is the frame at FA90, which is part of main. This is the program counter in main. And main will return to 40077150, which is like a library function by uclibc. And then here are the saved registers in main. Now, these are the frames reported by the debugger, I want to show you how the frames look like bare bones in the memory. And I use the examine command to inspect the frames in bytes. The examine command is a single letter command which has several permutations, is superbly powerful. To examine any part of the memory, you use the command X with a slash at the end of it. So X slash, now you have a very cryptic set of symbols. And I'm going to say X32XW. And I'm going to say, look at this saved register BEFFFA50. Oops. What does this mean? This means examine 32 elements of memory in hexadecimal, which are 1 D word each. So this means like 32 D words of memory in hexadecimal begin in at address BEFFFA50. This is the memory view that you see. Now, here at FA50, you see this is the pointer to the calling frame. Is at FA8C. And this is FA8C over here. This is the return address, 1128C, which belongs to main. Now, let's continue further. I want to do an info breakpoints. After this, info breakpoints is going to tell me which breakpoints have been hit so far. It says that breakpoint, the first breakpoint at web has been hit 1 time, and the second breakpoint has not yet been hit at log. I'm going to continue. And I go to log. Now let us do a backtrace. We're at 107 EC in log. Return address in web is 10AB8. Return address in main is 1182C. Again, we're going to now do an info frame. Here it tells us that the registers that were saved, R4 is at FA18, R5 is at FA1C, R11 is at FA20, link register is at FA24. And this was called by frame at FA58. If you look at where this frame at FA58 is, it is this frame. So web has now called log. If we follow the frame chain, if we look at info frame 1 and info frame 2, the topmost frame is for web. This was called by log. This was called by main. Let us examine the frame for log. Now the frame for log, we're going to pick this one where the first save register begins, FA18. X32XW, 0xBEFFFA18. Now this is the frame for log. Here is your return address. at FA 181C20 and 24. This is your return address to web. And this is the frame that is called, belongs to web. And then eventually this frame points back to this frame will then point back to main, this one. Okay. So this was just an overview of how we look at frames. Let us look at these return addresses in greater detail. We'll do info frame once again. These are the return addresses. What I want to show you is where I want to show you some disassembly. I want to show you where this function calls and where the return addresses live in the assembly code. Let's map it to the code itself. So if we disassemble web, keep in mind this return address from log 10ab8 belongs to the function web. So we're going to disassemble this function web, and we're going to find out what instruction is at 10ab8. Now, you can use the command disassemble web. It's going to give you a big disassembly dump, and go and scroll until you find instruction at 10ab8. And we'll place this in the live notes. One zero AB8. Scroll. I'm going to scroll to the very top first. Now, whenever you're looking at disassembly of a function, you'll typically see a number of instructions which manipulate registers, and every now and then you'll see like a branch. And these are colored in blue sometimes. So you have BEQ, that is a branch. We have BL, which is a branch with link, BLE, branch link. If equals, BGT, branch if greater than. So these are all these branches. And with each branch, it'll tell you which function is being called if it knows the symbol. So from the top, like here, it's going to call read. Then this is going to call a function within, it's going to branch to somewhere within web itself. This is going to call this is going to call log. And similarly, if we go to 10ab8, there is 10ab8. This is the return address. Immediately above the return address, you find this one. This is branch with link to 107cc, which is in log. That's where we are right now. And once this function returns, you'll return back over here at 10ab8. If we disassemble log, more disassembly, we will see this arrow over here. This is where we're currently at. We're within log, we're at a breakpoint, and we're waiting for further execution. And there's again like number of branches that happen over here. There are functions like getPID, sprintf, another sprintf, string length, write. So this is where some parsing and output writing is happening within log. We are going to now inspect the arguments that are passed to log. Like I mentioned, the arguments are going to be passed using registers in the ARM architecture. So if I dump the context, you dump context, and let us study these R0 through R3. These seem to be the arguments that are being passed to log. So you have request, this is a string, and then you have this get, blah, 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 blah. And so on. Within the function log, we saw a number of these functions, library functions that are getting called. You saw sprintf, you saw strlen, you saw write, you saw open, and things like this. Since we're looking for a crash, I'm going to kind of skip ahead a bit. We would like to set some breakpoints on functions which look very suspicious, which are memory unsafe. And we're going to try and set a breakpoint at sprintf. Whenever sprintf is called, we want to print the arguments that are being sent to sprintf. Then we'll continue the execution over here. So I'm going to say break sprintf at plt. A new breakpoint is set. Now, whenever we hit this breakpoint, we want to dump the arguments. So sprintf will have, sprintf syntax is going to be like this. Sprintf, then you have a target variable, and then you have a format string, and then you have number of arguments that follow it. This is how sprintf is structured. So we want to dump the address of the target variable and the format string whenever sprintf is called. So we're going to use commands. I'm going to now use the printf command. Printf sprintf %x to dump an address, %s to dump the format string. Then I'm going to say the address is going to be in R0 and the format string is going to be in R1. So every time this breakpoint is hit, I want to use printf, dump the address of the target and dump the output of the string. And thanks, Costas, for the man page reference for printf. And then we'll continue, and then we'll end. And now we're going to continue. And we're going to inspect all the instances of sprintf that were called. So we saw two instances of sprintf that were hit. We see the first of them is over here. It is like info %s %s %d. Then it hit log. Then we'll continue. And it hit another breakpoint over here. More sprintfs. Again, info and HTTP OK. And now the function, the program is ended. So this completes part 2 of the debugging session. I'm most likely going to run out of my allocated 2 hours of time. I'm going to stretch this by another 10 minutes if you folks are totally okay with it. If you by any chance need to leave, then don't worry, this video is going to be recorded and it shall be posted. Part 3 is we're going to then look at the crash, and then we're going to zero in into the crash. So there is a buffer overflow here. We're now not going to use curl anymore. we're going to use the attack1 script to generate a very long HTTP request. And then we're going to see what happens in the debugger. And we're going to trace it and very quickly arrive down at the crash. Okay. I'm going to run attack1 just to see what it looks like. So attack1 will send like 1,100 bytes of A's in the URL. And this will be sent to the target on NWeb. Once again, we reattach GDB. And we're not going to set any breakpoints. We're going to continue. And we now want to see where the crash occurs. So I'm going to run attack1.py, pipe to netcat 192.168.100.2 and port 80. I'm going to paste this in the live notes for your reference. Here we go. The process ran and it received a segmentation fault. It crashed. We control the program counter. Our stack is corrupted with a whole bunch of A's. We cannot get any backtrace. We cannot get any frames. Because the stack is corrupted, all the frames are corrupted. So we don't know where we are. Our goal is now to narrow down where did we crash? We of course crashed in NWeb. Okay, now did we crash in main? Did we crash in web? Did we crash in log? One of the three. Within each function, where exactly was the buffer overflow instantiated? What caused the buffer overflow? Is it in sprintf? Is it a string copy? Is it a custom written loop? We want to now narrow down from functions to individual instructions and see how this is going to be. We're going to take a quick and dirty approach in this one. First, we will trace each and every function. PLT, built-in function, whatever it is. Let's trace and dump everything to a file. And with each function breakpoint, we want to dump the backtrace. We want to see what the frames are like. And then we're going to attack it with the buffer overflow in the hope that we spot possibly at what juncture did the stack memory get corrupted. So once again, once we attach, we are crashing. I'm going to quit GDB, run it again. And dump info functions. We want to set a breakpoint at each and every one of these. So we'll just use, actually, let me do a little better. We don't want to bother setting a breakpoint at log, web, and main. Let's go down all the way to these PLT functions itself. Let's just set breakpoints at all the PLT functions, because each PLT function is eventually going to be called by log, web, or main anyways. And we'll discover that in the call stack. Just makes our process a little sharper. So I'm going to set rbreak PLT $, which means set a breakpoint at every function which ends with PLT. Boom. We got about 26 different breakpoints set in one go. It's great. And now for every breakpoint, we want to associate commands with it. We're going to turn the logging on, set logging on. I'm going to write a line over here separating each thing. Then I'm going to dump the backtrace. I'm going to set the logging off. Continue and end. I'll paste these in the live notes for your benefit. Now let's dump all this output to a file. Set logging file. We're going to put temp and trace2.txt. To continue. And now we'll run attack 1. We're going to see a whole bunch of activity happen. Here we go. And then we get this big, massive crash. I'm going to give it a couple of seconds, and then we will inspect the crashes together. And look at the crash and tell me, where do you find the first, where's the first instance that you see frames being corrupted? Let's look at this together. Here's trace 2. So first, it was fork, close, read, sprintf, called by log, called by web, called by main. Then immediately after this, you have open, log, and look at this. Log has nowhere to return to. When sprintf was called, log had something to return to web. So somewhere between the call to sprintf and open, the stack got corrupted. And from here onwards, it stays corrupted. Now, it will keep reporting this until log returns. And when log returns, you get a segmentation fault, you get a crash, and because the stack is corrupted, you control the program counter. Now, we're going to keep in mind the addresses where we're going to keep in mind these return addresses. Where they go? These return addresses. So sprintf was called just before 108F4 in log. We're going to set a breakpoint at log. We're going to then disassemble log. We're going to set a breakpoint at 108F0 just before sprintf was called. And then we're going to do some frame inspection and see how the corruption takes place. This is going to be the last part of the debugging session that I had in mind today. Quit. We're going to attach GDB once again. Let us set a breakpoint at log. And we will continue. We will then attack it using the attack script. And reach this breakpoint. So far, so good. Nothing has been corrupted. We want to check out that return address that we made a note of, 108F0. So we're going to disassemble log, and we're going to look for instructions at 108F0. I'm going to paste this in the live notes as well. And then we're going to set a breakpoint at 108F0. 10. There we go. 108F0 is a call to sprintf. Yep, that is the sprintf that is going to create problems for us. And this is the return address after sprintf, which we saw on the frame 108F4. Now I'm going to set a breakpoint exactly at this address. I mean, to set a breakpoint at a hex address, you use the star notation and the address by itself. (108F0). So breakpoint is set. And now we continue. We're going to arrive at sprintf. Look at the arguments that are being set to sprintf. R0 is the destination. It contains some string which will be overwritten. R1 is the format string info %s %d. R2 is the first of the strings supplied to the format string, which is going to be request, which is going to be substituted to the first %s. R3 is this big giant get request that we sent. Is going to be set over here. And then we have %d, which is 80, which will come in later on. This is the target memory address. Make a note of this address, BEFF614. This is the destination where the whole thing is going to be written to. If we inspect this memory address lives on the stack. BEFF is a high memory address. It lives on the stack. And all this format string assembly is going to be dumped into a variable on the stack. This is 1,100 characters long. So clearly we have a chance of a good stack overflow. Scrolling further down into GEF, so we're now waiting at sprintf, and GEF sometimes will detect built-in functions like, oh, hey, this is sprintf. I know this library function, and it'll automatically parse the arguments for us, which is a nice luxury that we get. If you want to inspect what R3 is, you can do x/s $R3. The S stands for examine string. And say that, okay, x/s $R3 is a buffer, which is get, and A repeats 1,100 times. We're still not executed sprintf. We're waiting to branch into sprintf. Let us study the frame. Info frame. So return, we are at 108F0. Our return address is at 10AB8. And if we dump the stack from address FA18, where the registers are saved, it's going to dump 4 values, not 32. you'll see the return address is saved at the very end in this hex dump. Is that FA24, and the return address is 10AB8. Keep an eye on this. We want to also dump the memory beginning at this buffer address, BEFF F614. We want to dump the memory from here, and I'm going to show you how to use hex dump for this. And the number of bytes we want to dump from BEFF F614, we want to dump to FA24. This is like the size of the stack that we want to dump. So I'm going to use hex dump. We want to see bytes. The size is hex 420, and the start address is BEFF F614. This is going to be the destination variable before sprintf. We're going to then do the same thing after sprintf and see what changes have happened. Now, this will give you a lot of output. If you scroll up at the top, this is the beginning of the variable, contains some memory that is left over. At the very bottom, at FA24, these 4 bytes, 100108B8, this is the return address in little endian mode. It's written in reverse when you dump it byte by byte. We are now going to step over sprintf. If you do a context, in this code section of the context, you see that this is a branch. If you step into, then you will go into debugging sprintf. We don't want to step into sprintf. We want to step over sprintf. So we will use next I as the next instruction. This will let us step over sprintf instead of going into sprintf. Now, after you do next I, sprintf is over, and now we are at 108F4. But things seem to have happened over here. Number of things seem to have happened. So let me now look at that corrupted frame once again. We go back to the hex dump. Use the up arrow and go back to the hex dump. Now you see this whole thing. You go to the very top. The info, request, and this get, this big gigantic string got written in. These 4 bytes used to contain the return address 108F, 108. What was it? I forgot what it was. 10AB8. They got corrupted, and now it's all 41414141. If we do an info frame, now you see your current program counter is 108F4. Your saved program counter got overwritten because of the stack corruption, and now it is 41414140. If you do a backtrace, you'll see that from log, you have nowhere to return to. And if I continue from here onwards, you'll end up hitting the crash. I'll take a minute of pause over here. I'm going to recap what we did. We started off with basic debugging. We saw a few of GDB's features in how to footprint a binary, how to trace through basic execution, discover the functionality of a binary, identify which functions get called in which sequence, hit tracing, identify which arguments are being passed to the function, look at which library calls are happening, study the frames, study the stack memory, and also we did a very little bit of crash dump analysis, enough to get us to the root cause that this is the exact sprintf which overflowed this buffer within the function called log within nweb. And we did this all without using the source of nweb. We simply used GDB and a few commands of GDB and GEF to work our way through the disassembly sessions. From this point onwards, you can write a nice exploit for nweb. You've got control of the stack memory. That's an entirely different thing, which I typically teach in my class onwards. We're a lot out of time. The one thing I do want to tell you is the same nweb binary exists in the damn vulnerable MIPS router. If you wish to follow this entire process on the MIPS architecture, I highly encourage you to do that. In the launcher, instead of starting damn vulnerable ARM router, start the damn vulnerable MIPS router. Follow the same process. You'll have different registers. It's the same GDB, the same EMUX GDB approach, and you'll get very, very similar results. It is the same binary, which is instead of being compiled for ARM, it's being compiled for MIPS. A last thing, as a matter of housekeeping, whenever you're finished with an EMUX session, cleanly halt the emulator using EMUX halt. This will shut down the kernel, unmount everything. You may kill the window close, but sometimes there's stale file handles that get left behind, and that results in some weird data corruption. Not often, but it is non-negligible. It occurs with a non-negligible probability. All right. I'm going to take 5 minutes to conclude this workshop. What we saw, I recapped, we saw how to use EMUX GDB. We saw a little bit of GDB use. We covered a number of these GDB commands. We showed you what they do, and we showed you where in the whole process do these commands fit. And lastly, where do you go from here? If you're interested in more of this, go play with EMUX. You already know where the code is. There's documentation available on emux.exploitlab.net. Look at some previous workshop videos. Follow my Twitter handle for any more announcements about EMUX. If you're really, really interested and you want to learn a lot more about this, you may still sign up for the ARM Exploit Lab, which happens on the 6th through the 9th of August in Las Vegas. For those of you who are attending, tomorrow you will get a little present delivered in your inboxes as our way of saying thank you. There's a lot more that we can cover, both with GDB, with EMUX. Hopefully, what I did today gives you an overview and a good start. I hope those of you who are following along were able to get their hands dirty and get through the whole practice session that we did together. Before I wrap up the workshop, I would like to go around the floor, ask you folks if there are any questions that you may have that I can answer for you. Have at it, raise your hands or type it in the chat boxes. We will also share the live notes. If you're going to the live notes, you can click the download button and grab a copy of the entire transcript that I've pasted on the live notes. And at the end of the session, Cherry or I will share the snapshot of the live notes into Discord. Right, folks. Any questions that you may have? Or one new message, let me check. Oh, hey, thanks, Fernando. Thank you very much. Last round for questions.